Okay, so moving on to question 84, give the products of the following acid-base reactions and indicate whether the reactants or the products are going to be favored at equilibrium. There are actually four of these sub-questions, A through D. I'm just going to go through two of them, and then you'll need to go through C and D on your own. But if you can understand the way that we do A and B here, C and D should be relatively trivial. Okay. All right, so let's do question A. So we have our two reactants on the left. So the first goal is to figure out, in an acid-base reaction, which of these two compounds will act as an acid and which of these two compounds will act as a base. So in general, this is a relatively simple thing, especially whenever you have a charged and an uncharged species shown together. So for this case, this is a pretty simple scenario because we have a negatively charged methoxide and we have a neutral carboxylic acid. So we can do this the intuitive way first, and then we'll do it the rigorous numerical way. So one of the things we said before was that if you have a negatively charged atom, if you have the same atom, if you're comparing the same atom, then in general having something that's negatively charged is going to make it more basic than having something that's neutral or it has no charge. So in this case we're comparing kind of apples to apples, but not really. But so thinking about this oxygen that has a proton, this is neutral, versus this oxygen right here that has a negative charge. So it's going to be negatively charged and basic, relatively basic. So on an intuitive level, it should, you should approach this going in thinking that, well, the methoxide is probably going to be more basic. It's probably going to be acting as the base. Okay, so we can do that in an intuitive way. The second way is if we wanted to, do a more rigorous analysis, we could compare pKa. So if we know a pKa number of two different compounds, then, well, we can compare directly the acidity and hence the basicity. So, but in this case, we only really know one pKa value, and that's for the carboxylic acid. So that's, that pKa is going to be around 4 for this particular acetic acid, or this particular carboxylic acid. This is acetic acid. It's going to have pKa of 4.7, so just somewhere in there, 4 or 5. But I just happen to know the specific one for this one. And we don't even have a proton associated with this oxygen. So in a in a really rigorous way, there is no pKa to give. So there isn't a pKa to actually compare it to. We could technically talk about the acidity of these hydrogens that are attached to carbon, but those are going to be extremely non-acidic, so not really even worth talking about. So between the two, it should be obvious that this methoxide is going to be the base, carboxylic acid, simply also because of its name, carboxylic acid, it's going to be acting as your acid. Okay, so the first thing that we're going to do is we have our reactants. Let's figure out what the products are going to be. So in this case, this is where being able to draw arrows, being able to talk about how electrons move is going to be really, really useful, and actually it's going to be an extremely essential skill to have. So let's go ahead. We'll start by using the electrons that are surrounding this negatively charged oxygen, and I can draw them out specifically. So we'll have 3 different sets of lone pairs, and so you can either draw the origin of the arrow starting at the lone pair, or you could have it starting at the negative charge. Either way is really acceptable. So I'm just going to use this lone pair just because. So this is going to be our base. We're going to be using this oxygen, or the lone pairs on the oxygen, to pull off a proton from the carboxylic acid. So again, the base of the arrow is where electrons start. The head of the arrow is where electrons end. And what we're really showing here is we're showing the formation of a new bond between this oxygen and the hydrogen. So the mantra that we'll hear over and over and over again is, if you make a bond, you must break a bond. And this mantra is going to be pretty universal. There are some exceptions where we don't have to break a bond. You can think about it as you really have to follow that make a bond, break a bond mantra to avoid breaking either the octet rule for carbon, nitrogen, oxygen, or for breaking the duet rule for the hydrogen. So in this case, if we didn't break a bond, we would have 2 4 electrons surrounding hydrogen and hence be breaking the duet rule. So we can't do that, so we have to follow that mantra. If we make a bond, we have to break a bond. So The bond we're going to break is this oxygen to hydrogen bond, so we're just going to break that bond. So what we're saying again, electrons start at the base, electron end at the head. So we're using electrons from the oxygen to hydrogen to, break that bond, and we're pushing those electrons onto the oxygen. Okay, so what will our products look like? They're going to look like this. We're going to have our carboxylic acid, which has actually lost a proton. And at the beginning, this oxygen on the left had 2 lone pairs. So we'll retain those 2 lone pairs. But then now we've used the electrons in this oxygen-hydrogen to push electrons onto the oxygen. So now we actually have not 2, but 3 lone pairs. Okay, and now also you can do a quick charge calculation in your head and find out that this oxygen is going to be negatively charged. So the charge calculation in your head should go 6 minus 246 minus 1, so 6 minus 6 minus 1 is going to be negative 1. And it should really literally be that quick. If it's not that quick for you, you need more practice. Ideally, that's how quick you should be able to do these kind of calculations. Okay, and then the other species for our product is going to be the protonated methoxide. So we're going to have that hydrogen that used to be around the oxygen on the carboxylic acid, and now that's going to be attached to the oxygen that used to be on the methoxide. So let me just redraw these guys just to be really rigorous. This red hydrogen is now right here. Okay. Sometimes it's easy to lose track of where atoms end up going. Okay. So all right. So we have our products. We can double check charge balance on both sides of the equation. So overall we have a negative charge on the left. Overall we have a negative charge on the right. Okay. And the charge used to be on the oxygen on the methoxide. Now it's on the oxygen on the carboxylic acid. Now this guy's actually no longer called a carboxylic acid. It's technically called a carboxylate, but that's for later. Okay, so step one's done. We've drawn our arrows. We figured out how we're transferring protons around, and now the goal is to indicate which side of the equation is actually favored, which side will have the more predominating species. And this is actually an extremely simple problem. We simply have to compare pKa's. So if you think we figured out which compound on the left is the acid, so that's going to be our carboxylic acid was our acid. It's the one that's actually giving up a proton. And let's say if we were going from right to left, if we were going in the backwards direction, how would this work? Well, now we have our acid bases being flipped. So now the carboxylate is being the base, and our methanol is acting as an acid if we wanted to go back to the left. So the way you would represent that is you would take the electrons from the oxygen, make a new bond between the oxygen and the hydrogen, and you would break the bond between the hydrogen and the oxygen. Okay, and so if you did this thing if you did these yellow arrows, that would take you back to the left. Okay, so now of these two, the acid is actually being, the methanol is acting as the acid. So our HA is on the acid, on the methanol. And so now you actually have to be able to recall pKa values. So those should be completely ingrained in your head by now. They should be like second nature. So we know that pKa of a methanol proton is around 15. And so now we have our acid on the right and we have our acid on the left. Okay, so now if we were going to figure out which side of the equation is predominant, we have to say, well, which one's going to be more acidic? And you now have to remember, okay, the more acidic compound is going to be the compound with the lower pKa. So of the two, this is going to be the lower pKa. And so if you have to compare acids, the carboxylic acid is going to be way more willing to give up a proton than the methanol. And so in this case, the equilibrium is going to shift more to the right. Okay, so if we were going to draw arrows, we'd have to draw equilibrium arrows that looked kind of like this. So this arrow is going to the right if we, deprotonated the carboxylic acid, and if we were going back to the left, that would be indicating the deprotonation of the alcohol. So that's what this guy would look like. Okay, and so what I'm indicating here is that you see how this yellow arrow going to the left is way smaller than the blue arrow going to the right? That's the way of saying that, okay, it's going to be, the reaction going to the right, the deprotonation event going to the right is going to be way more favored than the deprotonation event going to the left. Okay, and so that's all there is to it, really. So what we can say is that equilibrium will favor the weaker acid. So in this case, our stronger acids on the left, our weaker acids on the right. So using that guideline that equilibria will favor the weaker acid, then the equilibrium should shift to the right. Okay? So let's do one more problem. We'll do the second one, and I'm not going to go into as much detail. I'm going to do this as if I was actually working this problem for, let's say, a test. So first step, find the acid. Acid is going to be your methanol. So this is going to be our acid. This is going to be our base, our amide, negatively charged. So pKa for the alcohol is 15. So then we'll have to do our acid-base equilibria, figure out the products. We're going to use electrons from the amide. So this guy's going to have 1, 2 pairs. And one of the pairs is going to be used to deprotonate the alcohol. We're forming a new nitrogen-hydrogen bond. We're making a bond, so we have to break a bond. So we're breaking the oxygen-hydrogen bond. So our new products on the right are going to look like this. Negatively charged oxygen and then NH3. Okay? And so now, if we were to go back to the right, the acid would end up being this ammonia. Okay? So what we're going to have is we need to know the pKa of the ammonia. That's going to be around 40. Okay, and so if we were going to go back to the right, the way we would draw the arrows to form bonds is, well, let me redraw the ammonia real quick. We need to redraw the ammonia like this. H, H, H. Okay, and so if we were going to redraw the electrons moving from the oxygen to the hydrogen, we could draw them like this. And we made a bond, so we have to break another bond. So that's breaking the bond. And so that would reform the methanol and the amide. Okay? And so now, again, going with the mantra that the equilibrium is going to favor the weaker acid. The weaker acid's on the right. So in this case, the equilibrium will favor the compound on the right, or the ammonia as the protonated form. Okay? I'm sorry, yeah, it's going to go farther to the right. Okay. So if we were going to draw our equilibrium arrows, the equilibrium is going to go farther to the right. Very little of this ammonia is going to be deprotonated by the methoxide. Okay. So that's pretty much it. And so let's just think about this in terms of a practical thing. It's really good to put this in context. So it's not just a problem that you solve, but it's also, take something away from it in terms of what you should learn. So basically, all we're saying here is that up here, methoxide is a good enough base to deprotonate carboxylic acids, and amides, negatively charged nitrogen, is basic enough to deprotonate alcohols, but not the other way around. Alcohols are really poor at deprotonating amides. We actually would need something way more basic if we wanted to deprotonate this guy. And same thing here. If you really wanted to deprotonate an alcohol, it would be a very poor choice to utilize a carboxylate to try to do that. There are way more basic compounds that you could use to have that deprotonation going on. And right now this kind of it probably sounds a little esoteric, but later on this kind of decision making is going to be really useful for synthesis and problem solving. Okay, so again, you have 2 more problems, C and D, to do. Hopefully they should be pretty easy, yeah, good luck.